Saxon Algebra 2, Lesson 94. Students, today we're going to talk about functions. Functions are not something new and different. They're another form of language for talking about what we already know and understand really well. Let me prove that to you. This is something that you're quite familiar with. This is the equation of a line, right? This is the y-intercept. This is the slope. We can easily graph this. We know that we can choose values for x and then calculate what the matching y would be. Let's do that. We used to do this when we didn't know any other way to graph, but it's going to be useful for us today. X and y. And we know that we can choose any values we want for x, plug them in, and calculate the y. So let's do that. I choose 1. That's a nice easy number. I plug it in as the value for x. 2 times 1 is 2. Minus 3 would be minus 1. Okay? So I know that I could graph this, and it would be on this line. Let's choose another value. 2 times 0 is 0. Minus 3 would be minus 3. So here's another point that we could use to graph this line. And remember, the wisdom was choose 3 points. So let's do one more. Let's choose positive 2. And that would be 4 minus 3 is positive 1. Okay, so we know, we're not going to graph it, but we know that we could graph these 3 points, draw a line to connect them, and that would give us the line that we would call 2x minus 3, right? Okay, this is familiar ground. We've covered this a long time ago. What I'm going to do now is just lay some function language on you to show you how we can talk about old ideas in a new way. Instead of calling this the equation of a line, which is true, we can also call it a linear function. X we call the independent variable. When we were choosing values for x, we could choose anything we wanted, couldn't we? It was totally our choice. That wasn't true for our y's. We didn't choose our y's. They were what we call dependent variables, right? The value that we got for y depended on what we chose for x and the function itself, right? We combined the independent variable with the function, and we got the dependent variable. Okay, other names for these that we've talked about is that this is the domain, and this is the range. Okay, then we also know that we can represent the domain and the range with a different kind of picture, right? You've seen this before. 1, 0, and 2 are the numbers we chose for our domain, and the range that we calculated was minus 1, minus 3, and positive 1, right? I'm taking these numbers and these numbers, and we see that there's a connection. And there are different words we use to describe this when we're talking about functions. We call it a pairing, or a mirroring, or a mapping, or an imaging. All of those words can be used to describe this relationship between them. We say that every element of the domain, which I abbreviate with a D, has an image in the range, right? There's what we call, and this is kind of my favorite expression of all, is we say there's a one-on-one matching between the domain and the range. One-on-one matching. All of these verbs also describe this relationship. There's a pairing, there's a mirroring, there's a mapping, there's an imaging. That comes from this word image. Okay? A one-on-one connection. All of these ideas we need to talk about them directly, but you've been aware of them all along because you know this is an ordered pair, right? These are ordered pairs, and one goes with -1. You can't plug in 1 and get something different than -1. You're always going to get -1. So we're adding some new language to talk about the way the numbers behave, even though we've been watching the numbers do this for quite some time. What John wants us to do is talk a little bit more about that imaging or pairing that we see when we look at a function this way, right? We're used to thinking of equations as functions. We don't usually look at just the inputs and the outputs, right? The domain and the range. We don't usually just look at that. We usually look at this part. So when John has a lesson that focuses on functions, he's switching our focus ever so slightly from this part to this part, but it's all the same. It's all connected and it's all related. So what I want you to take away from this, besides the details I'm going to take you, is that functions are not new. They're just a new way of talking about what you already know. The reason this is a big deal is because a lot of students get to college level math where instructors like to talk about functions all the time, and they're like, oh no, we're doing functions. I don't know that much about functions. Yes, you do. You know a ton about functions. We just talk about them in non-function language a lot of the time. So this will help you bridge the gap so that when your teacher says, oh, we're going to talk about functions, you'll say, oh, I know about functions. They're a one-on-one mapping. So let's look at those one-on-one mappings. And there are a couple quick examples here. 1, 2, 3. 94.1. Okay, John says, which of the following depict functions? And he's got a bunch of these pictures for us. So I'm going to go ahead and draw the pictures. Here we go. Is this a picture of a function? And the answer is yes. Because each member of the domain, I'm going to say, this is a function because each member of the domain has one and only one image. It's a function. Let's look at another one. Okay, and our arrows go like this. 7 pairs with 3. 5 pairs with 3 and with 4. Uh-oh, no. This is not a function. And the reason why is that 5 has 2 images. Right? 5 is sometimes paired with 3, sometimes paired with 4. That's a deal breaker. So the answer to this one is no. Notice the difference. It's okay if they both point to the same number, but it's not okay if a member of the domain points to 2. See the difference between these arrows and these arrows? That's the difference between a function and not a function. C. Give you a second to catch up. This is the way the arrows go on this one. 4 is paired with 5. Beautiful. That's good. 6 is paired with 7. Perfect. Those are good images for both of them. The cheese stands alone. M does not have a buddy. So no, this is not a function. Because M has no image. Poor little baby. A little independent variable with no image, no pairing, no mirroring, no one-on-one mapping. It's so sad, isn't it? And here comes the last one. And this one looks different and it's confusing. The domain is described as the real numbers and then up above the arrow is written y equals x plus 2. Now, what are they even saying here? This actually is closer to the way we have approached our math than this. We have talked about the real numbers. We know that's all the fractions and decimals and everything in between. And we know that you can take those real numbers and plug them into an equation that looks like this, right? These are your domain, these are your independent variables. You plug them into x and you create the y. Is this a function? Yes. Because we can create an image for every member in the domain. This is just a general category, but give us any real numbers and we could run them through this and give you an image for it, couldn't we? We know how to do that. They aren't all listed and shown, but we know how to take real numbers and plug them into this and create their images. Every member of the domain can be imaged. We know how to do it. We just aren't writing out specific examples as we have in these. This is really much more like the way we have thought about functions up till now. We look at the equation and we plug numbers into it. So this is a valid way to diagram a function. All right? These look new and different. This is really what we've been doing all along. Okay. 94.2. This we've seen before. This is where John asked us a question about functions by showing us a bunch of pairs. I'm going to write the rule out and then I'll show you what I mean. Four little mini examples. Which of the following sets of ordered pairs of x and y are a function? Here's what we look for. Let me cover up the other one so we can focus better. If all of the x's, all of the first number in the pair are different, then we don't have to worry about it. It's probably a function. 4, 7, minus 3, minus 6. Okay, those are all different, so that one is a function. It doesn't matter what the other numbers are. The second one, 4, 5, 7, 6, also a function. C is where we run into trouble. Look at the first letters, 5, 4, 7, and 5. Aha, we have two 5s. If the x values are equal, the same, and they are, those two 5s, then the y's paired with them must also be the same. This 5 is paired with a minus 2. This 5 is paired with a 4. Warning, that is not a function because the 5s are not imaged with the same number. So C is not a function. And then let's look at D, 7, 3, 6, and 4. Okay, as long as the x's are all different, then it's probably a function. So A, B, and D are functions. C is not because 5 has 2 images. And that's what I'm saying here. Look for the same x, right? If there are none of the same x's in that group of pairs, then it's a function. If the x's are equal, then the y's must also be equal. All right, so that's the rule you need to use to look at those list of ordered pairs. Now, example 94.3 is a calculation problem, and this is something that you're very used to doing. We're changing the notation ever so slightly, but you've been doing these problems for years. 94.3 says this: if give you a second to finish copying and then I'll break it down. John is giving us two functions. Whenever we see this h of x, p of x, we know, oh, we're using function notation. We've done this usually writing a y in here, but John is using function notation, which is nice because it allows us to have two different equations that aren't necessarily in a system, right? It's okay if we have a system, but this is the h equation and this is the p equation. It's just a way of naming them, and it's convenient even if it is a little weird looking to our eyes. But we can call this equation h and this equation p. What this is telling us to do is take equation p and plug in minus 3. That's all it's saying, is plug minus 3 into this. We've been doing that kind of work for a long time. So we write, okay, the p of minus 3 equals, and then we take this and just put a minus 3 in wherever there's an x. Buckets matter. See how I did that? I just created buckets where the x's are, wrote the rest of the problem as is, plugged in the value that John wanted us to find. And again, it may be stressing the obvious, but this tells us just use the p equation. Ignore the h, we're not dealing with that. Now all we have to do is simplify this. Negative 3 squared is 9, and then this becomes plus another 9, and so we get an answer that says the p of minus 3, that's how we say that, equals 18. If the h of x is 4x minus 3 and the p of x is x squared minus 3x, find the p of minus 3. That's how you say that. It's kind of weird to say. But all they're saying is here's an equation, let's call it h. Here's an equation, let's call it p. Now plug minus 3 into equation p. That's all it's saying. This is the right answer. On the test, I would not give you problems like this. This is the kind of testing that I would do on this function lesson. All right, so please don't think of functions as something separate that we're studying separately from everything else. Function notation is a way of writing math problems, and function language is a certain way of talking about problems. And whenever you see this kind of language, pairing, mirroring, mapping, imaging, independent variables, dependent variables, you know that we are using our function language, okay? You can do it, it's not a big deal. Don't let that frighten you, all right? When you get to college and they say, hey, let's study functions, you're gonna go, let's keep studying functions, because I've been doing this for a long time. Okay, that's all I have to say about that. Thank you, bye.